Hi everyone, I'm Gauri Shivaji Zadav. I will be explaining workflow of the PMSM motor. Once we open the flux motor, we can see this supervisor interface. Here there are different motors templates. We can see here in which I have selected PMSM motor template. After opening this template, to design the motor, we have followed three steps: design, test, and export. Now we will start with design. From machine, we have from machine, we have three design parts: topology, housing, and shaft. In topology, we can see the winding technology. There is a two winding technology, classical winding and hairpin winding. Here I have selected hairpin winding technology. Hairpin winding has a shorter and more uniform conductor path, so it will help to reduce resistance and I square R losses. Again, we have the dimensions input. Here we have the three types of dimension inputs, like total outer diameter is a resulting dimension. Once we use the input, then software will automatically calculate the rotor outer diameter from first option. From second option, once we use the input, software will automatically calculate the air gap of a motor for second option. And for third option, once we give the input, software will be automatically calculated the stator inner diameter. So I have selected this air gap dimension, uh, uh, air gap dimension part. So this is the 8 pole 48 slot machine. So according to motor design, I have selected these inputs. So next part is a housing part. Housing part can help to protect the uh, inter inner part of a motor against the external damages. So in design, we have the circular and the rectangular housing. Here I have selected the circular housing part, and according to design, I have used the input. So we have the fins in housing design. We have the fins design. Here we have two options, like parallel fins and radial fins. Here I have selected parallel fins. To give the dimension of the fins, we have again two methods, like according to height and according to extension. Here I have selected height. Total I have selected, means I have given 30 fins. We can see here the fins. Then we have the circuit option. Here I have selected none, but we have the option like zigzag circuit, sinusoidal, and user defined circuit also. So next part is a shaft. In shaft, we have the design and bearing part. So for design and bearing, we have the two topologies, like none and with shaft and with bearing. I have selected for both with shaft and with bearing, and according to that, according to motor design, I have selected these inputs. So after giving these inputs, our motor shaft and bearing look like this. We can see here, this is the bearings and this is the shaft. So this in rotor design, we have the magnet design, means we more focusing on magnet design. So the magnet is produce the magnetic field necessary for the motor operation. So it is very important design part. So from the here we have the design option. From that we can select the new magnet, or we can select the magnet shape. Here we can see the different configuration for the magnet, and in that we can see the sub configuration. Here I have selected IMS ring 01A magnet shape. Once we select the magnet shape, we can change the magnetic thickness and the magnetic outer arc according to our design or according to our output. So once we gives the input, we can see the output. Here also we have the polarization. It is very important part because polarization decide the magnetic field direction. So here I have selected the coordination system as a global and the radial plus orientation. So we can see the um, magnetic flux direction of a magnet here. Once we Then we have the skew system. So here I have selected, we have the continuous skew and step skew option, but I have selected none option. Once we done all these things, we can see our design look like this. So we have the stator design also. For stator, we have a slot. In slot is a houses slot. It houses the winding and effects on magnetic field distribution. So it is we can select slot shape from these. Again, we have here different slot configurations. So and that in each configuration we can see the different slot sub configuration. Here I have selected OS free 01A slot configuration. So according to our motor design, we can give the input, and once we give the input, we can say we can see like see here we can see slot height, slot width, slot intermediate height, and all these options according to our uh, conductor number of conductor and winding configuration. We can design the slots here. So and this is once we give the input, we can see the output box here, and we have the lamination. Here we have the none option, circular and square option. Here I have selected the square circular option, and no need to give here we no need to give any input here. So we have skew option. I have selected the continuous queue, and we have the none option. I have selected none option. And then we have the winding configuration. So winding conducts current to generate the rotating magnetic field. So we have the different ribbon, means different parts in winding configuration. In scheme we can select the star or delta winding configuration, or here we have the definition modes like auto mode, easy mode, advanced and expert mode. Here I have selected as a auto mode. So anyone who is from non-electrical background can also design the motor after selecting the auto mode. So means after selecting the auto mode, software will it's select winding configuration according to design. So we have another option like easy, advanced and expert. In advanced and expert, we can gives the winding configuration, like we can set the winding configuration according to our design here. So this is the here I have selected number of parallel path 2, conductor 4, and number of layer is 1. So according to design, I have selected the width coil width height inputs, and I have uh, given that insulation material, winding, and all these things. So once we once we once we design the motor, we can see the view of our motor winding configuration. Here we can see the motor winding configuration view. Also we can see the phase wise motor configuration here. From here we can select the single phase, two phase, three phase, hairpin, back end, and all. Also we can select the conduct number of conductors and current direction, and we can see our um, current direction and our winding flow of winding. So this is the stator design. Then next is a cooling system. We have the external and internal cooling system. So, external cooling system dissipates the heat using external elements like fans or liquid cooling. Here we have the natural cooling and forced cooling option. I have selected the forced cooling option, and we can change here input like horizontal, vertical, horizontal OS up and OSC up. So here I have selected horizontal, and for radiation and X factor I have selected the auto mode. And for the internal, we have the natural cooling and forced cooling. I have selected here forced cooling. So internal cooling manage heat within the motor using internal airflow or cooling channel. So it can help to improve the efficiency and heat dissipation. So we have another part is a material. In material, we can see here we have the option like database. From this database, we can create our own material also. So here I have selected the already created material. For frame, I have selected aluminum 6061, which has the lightweight, corrosion resistance, high corrosion resistance, and good mechanical property. So I have selected for frame aluminum as a for material for frame. So for shaft, I have selected stainless steel because it has high strength and excellent corrosion resistance. And for the bearing, I have selected the carbon steel. Carbon steel means EN1191 because it has high hardness and wear resistance. So for the resistance, I have for rotor and the stator magnet circuit, I have selected as a electrical steel material which has the high magnetic permeability and low core loss. And the magnet shape I have selected neodymium, neodymium urban born, which has the high magnetic strength, good temperature stability. And for insulation, I have selected high thermal resistance material like Nomex 130. So for cooling purpose, I have referred air cooling method. So this is the first step of the this is the first step of the design we have completed. And for the next step is a test. We can see we have the different tests like characterization test, working point test, performance mapping test, and machine test. In this, we can see here we have the open circuit test. In this, we can see there is a two test, cogging and back EMF. Cogging torque is an unwanted torque which is produced by the motor. So we can here don't we here no need to give any input for cogging test. We can just simply uh, run this test. Once we run, we can see the result cogging torque. The minimum cogging torque is gives the more efficiency or better performance. So here we get the 3 Newton meter peak cogging torque. It is minimum. So and we get the magnitude of peak to peak cogging torque is a 6 Newton meter. So again we have the back EMF. In back EMF we can see mm, the input as a rated RPM. We need to give the input as a rated RPM. Here I have selected 3000 is a rated RPM. Once back EMF is a un it shows voltage induced in the motor. So here we once we run this test, we can see um, here motor voltage constants in Ke. It is a crucial for control the algorithm. So this value determines the motor ability to generate the voltage per unit speed. It should align with the design specification. Here we can see the phase voltage first harmonics is peak harmonic is 95.38 volt, and the line to line voltage harmonic voltage is 165.229 volts. The waveform consistency and harmonics distortion should be checked to ensure the smooth operation. So also we can see here flux density is 0 0.9 within a good range. 0.90 is within a good range, meaning effective electromagnetic coupling. So mm, again here we can see the this phase voltage versus time graph. Here we can see the back EMF waveform is good with the balanced sinusoidal shape, including proper motor winding and symmetrical design. So if the motor is here we can see the waveform cross zero at evenly spaced intervals, confirming that the rotor and stator alignment is proper and there are no electrical faults. So there is the uh, next test is also here we can see the ISO value of flux density of in each parts. And magnetic flux versus rotor position graph. So the next test is a model test. Mm, this model test it analyze key parameters like torque, speed, efficiency, and losses under different conditions. So to run this test, we need to give the input like operating quadrants, maximum line current or current. Here I have put this as a 50 and maximum speed as a 6000. Here we need to give the operating quadrants according to uh, our design. Here I have selected all because I have designed motor for EV purpose. So once we run this test, we can see the result. Here we can see the result. Here we can see the winding and magnet characteristics. So also we can see here the all maps and dual loss, stator loss graphs, and also we can see the machine mechanical loss here. We can see we get the zero mechanical loss, means it is good. So also we can uh, change the thermal, electronic, and mechanical setting. We can import the data also here. So from this test result help in optimizing the motor before exporting to flux or advanced analysis. So we have another test is a datasheet test. In datasheet test, we can give the input like maximum line to line current, maximum line to line voltage, and command mode. Here we have two command modes like MTPV and MTPM, means maximum torque per ampere and maximum torque per volt. When we go with when we run the test for the below rated RPM speed, then we need to go with MTPA, and for the above rated RPM speed we need to go with the MTPV. Here I have selected MTPA because we here I have run this test. We can means here I have run this test for below rated speed, means that rated speed. So once we run this test, we can see the base speed data here. Here we can see the operating mode as a motor and mechanical. We get the torque as a 29.85 Newton meter and the with 92.26 percent efficiency. Also, the main uh, uh, parameter we can get here like control angle and the line to line current and line to line voltage here, which is here we get the control angle as 2.875. That control angle we can use for the sine wave test here. We will see in sine wave test. Uh, Also here we can get the power balance, flux air gap, iron loss. Also we can get the ripple torque here. Here we get the ripple torque as a 9 Newton meter. Uh, Also we get the ripple torque curve, ripple torque graph and all these graphs, phase voltage graphs. We can see all this data here. So, datasheet test provides the quick evaluation of motor performance based on a predefined condition. It generates key motor characteristics like torque, power, efficiency, and losses without running detailed simulation. So, user can compare different design efficiently using this standardized result. This helps in selecting the best motor configuration before proceeding with advanced test. So the datasheet is important. So next test is a thermal test. In thermal test, we can see here we need input inputs as uh, losses data. So that losses data mm, we get from the sine wave test. So that's why we need to run first sine wave test. So in sine wave test we have the um computation mode as accurate and fast. Once we go with accurate, we can get the accurate result, but it will take some more time. So and one more important thing is here we need to put the control angle. That control angle we get from the data sheet. Here we can see from data sheet we get the control angle as a 2.875, and that control angle we need to put here, and uh, we know the rated RPM as a 3. Here we have means I have the rated RPM as a 3000 RPM. So I have used this input according to motor design. Once we run this test, we can see the results like machine performance in main result working point, machine performance at a working point. We can see the machine performance at a working point. We get the mechanical torque as 31 Newton meter with 94.84 efficiency. This sine wave test analyze the motor performance at a specific operating point under sinusoidal voltage supply. So this test helps in understanding motor behavior under nominal operating condition. So under nominal operating condition, we get the 31.11 Newton meter torque with the 94% efficiency at 3000 RPM speed. Also here we get the ripple torque. We can see the torque versus rotation position graph. Also we can see the ISO value. Here we can see the ISO value at a different part. Also here we can see the torque, flux density, phase voltage graph, phase current graph. So next we have the thermal test. Uh, For thermal test input, we can import that input from the uh, sine wave test like this. And once we import this input, we can run this test. Once we run this test, we can see the result. In thermal test, we can see means thermal test evaluate the motor's temperature distribution under continuous operations, ensuring it means thermal limits. uh, Here we can see the motor means temperature of each part, and in radial wave view as well as in axial view. Also, we can see in this chart, we can see the final temperature at a different parts like shaft, bearing, and all this part. So this temperature test helps in optimizing the cooling strategy to enhance motor reliability and reliability and performance. So we have the performance mapping test. Again, we have the sine wave performance mapping test. The performance mapping test with the sine wave analyze the motor behavior over a range of operating conditions under sinusoidal voltage supply. It helps in understanding the motor efficiency, torque speed characteristic, and loss distribution across different working point. Here we need to give the we have the we need to give the maximum speed as a input, and here I have put the 6000 is the maximum speed, and we have again two mode command mode like MTPV and MTPA. So here I have selected MTPV for the above rated because here we need to check the motor performance at above rated or base speed. So once we run this test, we can see the base speed result as well as the maximum speed point result. Both point we get the maximum efficiency 97.46. Two also we can see the torque versus speed graph. Here we can see the torque versus speed graph. It is a const. We can see the torque versus speed graph is a constant. So we get the constant torque at till 6000 RPM. So this test is essential for optimizing the motor operation across different load and speeds. So at the last mechanics we have the NVH test. NVH means NVH test evaluate the motor's noise, vibration, and harness means harmonics characteristics to ensure the smooth and quiet operation. It helps to identify unwanted harmonics, electromagnetic force, and structural reasonable effect on the motor performance. So here we can change the mechanics and thermal. Also, we need to put the input as a control angle. Whatever we get in data sheet, we can put here. Whatever control angle we get in data sheet, we need to put here, and we need to run this test at a rated speed with the line to line current, rated line to line current. Once we run this test, we can get the result. Like we get the we can see here we get this overall sound power level is 44.22. So it is reasonable, but lower noise is preferred for quieter operation. Also we can see the Maxwell pressure graph here. You can see the mechanical angle versus rotor position graph here. This blue dialog line indicate the pressure variation which correlate with the electromagnetic force distribution. So we get the different value at a different rotor position. So and the Yes, we get these values. Also, we can see the sound power, sound power versus engine order. We here we can see the sound power at a different engine order, and we have the option like we can select engine order or frequency. Here I have selected the engine order. So um, so overall this NVH helps uh, to identify the vibration, noise, and harmonics resource and optimizing the motor structure for reduce NVH effects. So the next step is the for design. Next step is the export. In this we can export the report as well as the Python script of the design or motor. So to export the motor, we need to select whatever data we want to export. We can select that data, and for test also. And we have the material, and we have the this archive and the export information. For the export information, we need to give the name, and we have the format like HTML and PDF format, and here we can select the destination folder, means we can select the folder here, and the attached to motor we have two options, yes or no. Yes, once we select this, we can preview our motor report before export. Here we can see, means we can preview the report before exporting. Once we done, or once we uh, done this preview, we can go with the export option here. Then we can select this model for further analysis in HyperStudy, Flux 2D, SKU, Flux 3D, Flow Simulator, and we have this system option. We can export the lookup table in various format. So here export the 2D motor, here I have exported for the sine wave. In for further analysis, I have exported the motor in 2D, Flux 2D for sine wave, and here we can change the thermal setting also. Here also we have the conductor representation, basic, one open phase or all phased wire. Here I have all phase, so I have selected the all phase wire. And again we have the export information, like here we can change the export information as uh, we can change the export information according to, and we can select destination. Here we can give the periodicity. If you want full model, you can go with no. If you want periodic model like periodicity, then go with S. Sorry, if you want full model, go with S. If you want the periodic model, then go with no. Once we go done, apply all inputs, then we can export model in 2D. So here I have exported the model from FluxMotor for further analysis. Here I have done the iron loss computation. To compute the iron loss, we need to first define the laminated material. In physics, we need to define the laminated material. In laminated material, we need to select that iron loss, or we need to select the method of iron loss computation. Once we define the material, or we need to solve the model. After solving, in computation we can see the tab as a compute of iron loss on a electrical sheet metal. Once we select this, we need to select the laminated face region. Whatever lamination we have given, we need to select that laminated face region. Also we have the mod means we have the methods to compute the iron loss. We have mainly two methods like modify Bertotti method and the laminated sheet method. Here I have selected the modify Bertotti method, and whatever value we define in lamination type material, that we need to give here. Once we give that value, we can we get uh, the result. In post processing, we can see the result here, iron loss. We can see the value of iron loss. Total iron loss is 0.028, or also we can see the iron loss curve here. This is the iron loss curve. Also also we can calculate the total iron loss from here, because we get the iron loss like this, total iron loss like this 0.028 watt, but we have the periodicity, so we need to multiply here with 4. Once we multiply, we get the 0.011 watt is a total iron loss value. The computation of iron loss, which can help which can help to analyze losses like hysteresis and eddy current, which helping us to optimize the motor efficiency. The minimum loss indicates the high efficiency, so here we get the minimum loss. Also here I have done the magnet loss computation. So to compute the magnet loss, we need to first define the loss sensor. Here we can define the loss sensor. We need to create the loss sensor. Here I have created the magnet loss sensor. Then we need to define the magnetic phase regions here. Whatever magnet we have, we need to select that phase region. Once we create the sensor, we need to display that sensor. Sorry, once that we need to evaluate that sensor, or once we evaluate, we need to display the curve. Once we display the curve, here we can see the curve of the loss, like look like this. We can see the curve of loss. Also we can see the value of that loss is here. Like we get for first magnet, we have here periodicity. In we have the uh, that part, we have two magnets, so we can see here we get the magnetic loss, like mean value is a 2.03 e raised to minus 4. To calculate total magnet loss, we have the 8 magnet, so we need to multiply that value into 8, so we get the 0.01, 0.0016 watt is a um, magnet loss. For efficiency computation, we need to compute the input and output power. So to compute the input power, we need to, after solving, we need to go with curve, or we need to define the new curve according to according to here circuit values. The for the computation of input power, we need to calculate the means each conductor's multiplication of current and voltage of each conductors. We have three conductors. We have defined that three conductors, and we need to use this formula for the computation of input power. And for the output power computation, we need to follow these steps, but we need to use this formula. Once we use this formula, we can easily find the input and output power. Here we can see the graph of electrical input power, and to see the value of input power, we need to go here. In post processing, we can see the rectified mean value is it is approximate 9.1 kilowatt as a input power, and for the output power, also here we can see the output mechanical power, and the value of output mechanical power we can see here. This is the in 2D curves, input output curves, we can see the output mechanical power. Here we can see we get the 9 approximate 9047 watt, means 9 kilowatt power. So we can calculate efficiency from uh, input power divided by output power. Here we can see we get the 90 of output power by input power, we get the 98% efficiency here. Also here I have checked the demagnetization effect on permanent magnet. So the permanent magnet can lose its property under high magnetic loading or high temperature. So under high temperature, it will decrease the remnant flux density of a magnet. Before importing the model for demagnetization, we need to change the winding temperature and the magnet temperature as a higher level. Here, before importing the model, I have changed the winding temperature as a 150 degrees Celsius and the magnet temperature as a 100 degrees Celsius. We can see here like this. So for the evaluation of demagnetization, we need to define the new material with the nonlinear magnetic description. So here I have created the NDFEB N45H nonlinear magnet described by HCB, HCJ and BR module. For that I have selected for I have selected these values, and for the consideration of demagnetization during solving, uh, we can't select means we can't check this box for the analysis of before demagnetization, means without we done this as a without, we can consider as a without demagnetization. And once we solve this and then we need, once we define this material, we need to assign that material with the um, mm, magnet in physics, the phase resonance and volume. Here we can see I have assigned that material to the magnet. Here we can see that material, and I have run this simulation. Once I have run, I get the, we can see in computation, we can see the evaluation of motor, evaluation of the demagnetization for the means uh, for the for the demagnetization analysis, we need to check this box, and for means without demagnetization analysis, we do not check this box. So in computation, with the evaluation of demagnetization, once we evaluate the demagnetization, we can see in spatial quantity, we can see the spatial quantity BR mean 1, that quantity Once we done this, we can plot the um, torque. This is the evaluation torque, evaluation curve for torque without demagnetization. And for the demagnetization, we need to select for demagnetization analysis means with the demagnetization, we need to check this box. Once we check this box, we can and once we check this box, we need to assign that this material with a magnet, and we need to go with a evaluation of demagnetization. Once we evaluate this demagnetization in parameter quantity, it means in spatial quantity, we can see the this is the BR2 BR mean 2 value, which is for the um, with the demagnetization analysis. So here we can see the with the demagnetization analysis, magnetic means with the demagnetization torque. So to do the analysis, here I have imported that uh, curve without the demagnetization. So here we have with the demagnetization curve, without demagnetization curve, and I have superimposes impose that both curves, so we can see the result here. Here we can see this is the demagnetization with the demagnetization curve, means that pink line shows the with the demagnetization curve, and the blue line curve shows the without the demagnetization curve. So here we can see the average torque without demagnetization is 27.4312 Newton meters, while it is 27.26 Newton meter with the demagnetization consideration. Means it shows the impact is minimal at 100 degrees Celsius, indicating good magnet performance. Further increase in temperature may cause more torque loss. So, so this was the workflow which I have followed to design the PMSM motor. I got 31 Newton meter torque with 94% efficiency at 3000 rated RPM. It states that the particular motor is suitable for EV application. So I have just want to conclude that the flux and flux motor are analytical tool that can help to design, simulate and analyze motor performance quickly and very accurately. It make quickly and accurately, making it best software for the motor design. So thank you.